Okay, yeah, I see it.
Mm-hmm. Yeah, I woke up early this morning and I suddenly remembered for some reason that I didn't post it. So I did that this morning. Okay, so let me go back to the beginning again. So as I said before, we talked about earlier in this chapter, or the previous chapter, I should say, about polarity. A bond being polar is one where there's a separation of charge between the atoms involved in the bonding. And we said that that occurs when one atom is more electronegative than the other. So as you can see in the case here of hydrogen chloride, chlorine is more electronegative than hydrogen. So therefore, the shared electrons would be on average be closer to the chlorine atom and further away from the hydrogen. As a result, you have what is called a partial negative charge appearing on the chlorine atom and a partial positive charge on the hydrogen. All right, so therefore we have a clear separation of charge within the bond, and therefore the bond is said to be polar. And we can actually measure the polarity of bonds. And there's a formula that you can use to calculate it, and that would be equal to nu. Nu is what we call the dipole moment. It's a measure of how polar the bond is, and that would be equal to the charge that would be on each of the atoms involved times the distance, all right? The distance that separates the two charges, okay? So this is the formula that is used to calculate it. You're not going to use this formula in this particular course, but I thought it was important for you to understand how we come to the numbers that we use to express the magnitude of dipole moments of bonds. Let me also say that not only do we have what we call dipole moments or polar bonds, but we can talk about a molecule being polar. We're going to talk about that shortly. We're going to talk about how do we determine whether or not a molecule is polar. So before we get onto that though, couple of things I want to say here. One is that the unit for measuring dipole moments is the Debye unit, uppercase D, right? So that's the unit that is used when you're expressing dipole moments. And one property of polar molecules, such as hydrogen chloride, is that they are affected by an electric field. In fact, they will align with an electric field. So if you look at this setup here, where you have an external circuit equipped with a switch, electricity source, and then it's connected to two electrodes, one positive, one negative. This is a negative, this is a positive. Then what's going to happen when you close the switch? Oh, and by the way, the molecules here, these electrodes are immersed in a substance which has polar molecules. I should make that point. And in this case, before you close the switch, what happens is that the molecules are basically aligned randomly. They're basically pointing in different directions in different three-dimensional directions. All right. So that's what happens before you close the switch. Now, when you close the switch, what happens is that an electric field will be produced between the two electrodes, and the molecules will line up such that, as you can see here, the negative end of the molecule will be pointing towards the cathode, and the positive end of the molecule will be pointing towards the anode, all right? And that's basically one property that is displayed by polar molecules, right? They align themselves with electric fields. And it is this concept that is behind the idea of liquid crystal displays that you would see in your calculators and so on. The images that you see on your calculator display is as a result of electric fields being applied a certain way so that the molecules will be aligned a certain way. And in some cases, if the molecules align a certain way, they absorb light, and therefore the images will reflect those regions where the light is being absorbed. All right, so that's another example of how a discovery in science, research, etc., can be applied to technologies that we find useful. Okay, so that's basically what polarity is all about in terms of how the polar molecules behave. Now, what we're going to look at is how do we determine whether or not a molecule is polar? So we know that all polar covalent bonds have a bond dipole. In other words, you can measure the dipole magnitude by using the same formula I talked about, the dipole moment formula. And that's because, of course, you have a separation of positive and negative charge between the atoms of the bond. Now, what we're looking at here is a case of carbon dioxide, all right? And in each of the carbon to oxygen bonds, you have a dipole. You have one dipole acting in this direction, you have another dipole acting in this direction. And as you can see, because the carbon dioxide molecule is linear, these dipoles would be in exactly opposite directions. Furthermore, the magnitude of this dipole and this dipole would be the same because this oxygen atom is identical to this oxygen atom. So therefore, what we'll have as a result is that this dipole will cancel out with this dipole because they're linearly opposed, exactly. And therefore, the net dipole moment for this carbon dioxide molecule is 0. And what that means basically is that this molecule is non-polar. Let me write this down here. Okay, weird. So carbon dioxide is non-polar because the total dipole moment is 0, and that's because the dipole here and the dipole here are equal in magnitude and they're linearly opposed, and therefore they will cancel out each other, all right? So that's what happens in the case of carbon dioxide. Now in the case of water, as you can see here, this is the shape of water. Now recall that water has a bend shape. And in this particular case, for this bond, the oxygen to hydrogen bond, you have this dipole acting in that direction, that dipole moment. And in the case of the other oxygen to hydrogen bond, that dipole moment will be acting in that direction. Obviously, unlike in the case of the carbon dioxide, these dipoles do not cancel out each other. All right. In fact, the net dipole would be in the direction shown by the pink arrow right here. All right. So therefore, as a result, in the case of water, water has a non-zero dipole moment. In fact, it has been measured as being equal to 1.84 dBi. All right. So in the case of water, because the dipoles do not cancel out each other, it has a net dipole moment. And therefore, in the case of water, the molecule is polar. All right. So basically, in order for you to predict whether or not a molecule is polar, there are a couple of things you have to know. You have to know the shape of the molecule, right? And then you have to look at the directions of the dipoles for the individual bonds in the molecule. And basically, you have to identify whether or not the dipoles will cancel out each other. If they cancel out each other, then the molecule will be non-polar, and therefore the dipole moment would be equal to 0. If they do not cancel out each other, that means that the dipole, the molecule will be polar, which means that the dipole moment would be a non-zero value, all right? Now, in some cases, you have to use your imagination, especially when it comes to the three-dimensional shape. So for example, if you were to look at a tetrahedral molecule, let me go here. Let me get rid of this here. So in the case of a tetrahedral molecule like carbon tetrafluoride, you have to really use your imagination to see the molecule in 3 dimensions, right? And then it's a perfectly symmetrical arrangement. And in the case of this bond, the dipole moment will be acting in that direction because fluorine is more electronegative than carbon. Same thing here, same thing here, same thing here, all right? So therefore, again, in this case, because the dipoles cancel out each other, then the net dipole moment for this molecule would be 0, all right? And therefore, this molecule would be non-polar. Now, let me just say something here. If I were to replace this fluorine with hydrogen, let's say, so let me erase this here. And let me put hydrogen here. Then basically, this bond would essentially be non-polar, right? Because if you remember, we said that if the polarity of a bond is between 0.0 to 0.4, if the electronegativity difference is between 0.0 to 0.4, then this implies that the bond is nonpolar for most intents and purposes. And in this case, the difference here is actually 0.4, all right? So therefore, this bond is nonpolar. And therefore, as a result, the net dipole moment would be a non-zero value because basically the dipoles will not cancel out each other because this dipole is acting in that direction, that is acting down, that is acting this way, but you have no dipoles here. So therefore, the dipole total, the net dipole moment total will be a non-zero value, which means that the molecule, in this case, will be polar. So these are the things that you have to take into account when you're trying to determine whether or not a molecule is polar. Some things here that you should follow in terms of steps to determine whether or not a molecule will be polar. Firstly, you have to look at the electronegativity values to predict whether or not the bonds themselves will be polar. And then you have to use the VSEPR theory to determine the shape. And then based on the shape, you're going to identify whether or not dipoles will cancel out to give a nonpolar molecule, or they'll combine to give a resultant dipole moment for the molecule. One thing I probably should add in this list here, and that would probably be the very first step, and that is that you have to draw the Lewis structure of the molecule, because in some cases, you might be given the formula for the compound or the molecule or the ion, and you're asked to determine whether or not the molecule is polar. So just to give you, let me go back to this again. Just to give you maybe one or two examples. Okay, so let me make up one right here. Let's say you're given, let's say you're given SCl6, all right? So we're going to go through the same steps as before. First, we have to determine the Lewis structure. So what's the group number of sulfur? Anybody? Well, come on, guys, wake up. What's the group number of sulfur? 6, okay. And for chlorine, what is the group number?
7.
7, and we have to multiply that by 6, so that gives you 42. So the total number of valence electrons is 48, which is equal to 24 pairs, all right? So we put the sulfur in the middle, surrounded with the chlorines. And then we put the bonding pairs, chlorine, 1, 2, 3, 4, 5, 6. Then we put the non-bonding pairs, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, all right? And of course, you have to calculate the formal charges, which for sulfur, excuse me, that would be equal to 6 minus half of 6 minus 0, so that gives you 0. And for chlorine, that would be equal to 7 minus half of 2 minus 6, that gives you 0. So there are no charges. So the next question is, what's the shape? And if you remember, I showed you a table. Let me see if I can bring it up here. Remember this chart? So basically, we're looking at, let me decrease this some more. Okay, so in the case of a central atom bonded to 6 other atoms, why is this cut off? Okay, so basically, if you have a central atom bonded to 6 other atoms and there are no lone pairs, then the shape is octahedral. So if the shape is octahedral, right, that means that you have a sulfur in the middle here, and you have chlorines where the X's are, right? What would you think would happen? Let me redraw that structure here. So it's a octahedral shape, as I said before. The sulfur is here. You're going to have chlorine, 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 and then up here you're going to have chlorine, and down here you have another chlorine atom. So you have a dipole acting here, a dipole acting here, dipole acting here, dipole acting down, dipole acting directly up, and then another dipole acting here. All right? So what's going to happen is that basically the dipoles will cancel out, right? Because, for example, this dipole here will cancel out with the one that's opposite to it. The same thing will happen here and here, and the same thing will happen here and here. So therefore, in this case, the molecule here would be nonpolar, and therefore the dipole moment is 0. So this would be nonpolar. So that's basically how you can make predictions as to whether or not a particular molecule is polar. All right. Okay. Any questions about this example? Any questions? Okay. Let me do another example and then I'll move on to discussing some more stuff. So let's say you're given, I think we did this one before, POCl3. I won't go through all the steps in terms of the Lewis structure, but let me just draw the Lewis structure here. The Lewis structure is P double bond O, Cl, Cl, and Cl, right? So this is the Lewis structure. Now in this case here, you have a phosphorus bonded to 3 other atoms. Well, actually 4 other atoms. So therefore, if the question of shape comes up, then you consult your table again. And according to the table, if you have a central atom bonded to 4 other atoms, then the shape would be tetrahedral. So the shape of this molecule here would be tetrahedral. Tetrahedral. And if you remember in a tetrahedral, okay. And if you remember in a tetrahedral arrangement, you're going to have this arrangement here. Now in this case here, because oxygen is different from chlorine, the dipole moments here, here, and here will be identical, but would be different from that dipole moment, all right? So therefore, the net dipole moment in this case would be a non-zero value, which means that this molecule is polar, all right? So that's basically how you determine the polarity of a molecule based on the shape, based on a Lewis structure, which ultimately would lead you to the shape based on the VSEPR theory. And then you look at whether or not the bonds polarities will cancel out each other. If they don't cancel out each other, that means that the molecule is polar. If they do cancel out each other, that means that the molecule is nonpolar. Okay, so let's continue our discussion. Now, what we're going to look at is a greater examination of how bonds are formed in molecules, right? We're looking at covalent bonds specifically. And basically, when this is explained by the valence bond theory, and this states that whenever you have a covalent bond that is formed, it's formed by the pairing of 2 electrons that are spinning in opposite directions in the region of overlap of the orbitals. So for example, in the case of the formation of the bond between the 2 hydrogen atoms in the hydrogen molecule, what you must have in order for that bond to form is the 2 hydrogen atoms coming into close proximity, and the valence electrons that they have in the 1s orbital will be spinning in opposite directions, and then they will overlap so as to form what is called a molecular orbital. And in the molecular orbital, as you can see here, the electrons will be paired up, spinning in opposite directions, which of course is what we saw when it comes to atomic orbitals. The same thing will apply when it comes to molecular orbitals, all right? This region of overlap will have a high electron charge density. And this has been actually shown to be true based on calculations, which of course we won't get into at this level. And what is found is that the more extensive the overlap, then the stronger will be the bond between the 2 atoms that are involved, all right? So that's basically what is involved in the valence bond theory. So to demonstrate this for a more complex molecule, we have the bonding in hydrogen sulfide. So this is a sulfur atom. In the valence shell of the sulfur atom, you have 3s orbitals and 3p orbitals. Now the overlap that will take place between the hydrogens here and the 2 3p orbitals that are singly occupied by electrons, right? So basically this p orbital here will not be overlapped with because that will have the 2 electrons. This will have 1 electron. In fact, let me draw them here. So the 3p orbital will have 2 electrons spinning in opposite directions. The 3pz will have 1 electron, and the 3py will have 1 electron. And as far as the hydrogen atoms are concerned, they will have 1s orbital and therefore 1 electron occupying it. And these electrons must be spinning in opposite directions compared to the electrons of the orbitals they're about to overlap. So when this overlap with this, you end up with this region here having the 2 electrons. And the same thing will happen in this region here having the 2 electrons. And this orbital, as I said before, will still have your 2 electrons in that orbital. So therefore, that would be the arrangement and the type of overlap situation that would occur in the case of hydrogen sulfide. Okay, so that's what happens when you have orbital overlap to form a covalent bond. So some important points here concerning this. Most of the electrons in a molecule remain in the same orbital location that they occupied in the separate atoms, all right? So basically, the electrons that are occupying a particular orbital before the overlap will occupy the same position after the overlap. Bonding electrons are localized in the region of orbital overlap. And for orbitals with directional lobes, such as the p orbitals that we just saw, then the maximal overlap occurs when the atomic orbitals overlap end to end, all right? And that is, you can find a hypothetical line joining the nuclei of the bonded atoms passing through the region of overlap. So to go back to the previous slide here, what they're saying here is that the region of overlap, for example, let's take this region right here, right? Let's take that region. Then if you can draw a straight line from the nucleus of the hydrogen atom to the nucleus of the sulfur, if you can draw a straight line with, that crosses right through the region of overlap, then basically that bond would be a relatively strong covalent bond. Now, the reason why that is mentioned is because you can have other situations where that's not the case, where you cannot draw a line straight through the region of overlap from one nucleus to the other. And we're going to talk about that later on when we get to a discussion of the difference between a sigma bond and a pi bond, all right? So that's for later on. Now, before we get to that, however, let's talk about this particular concept of hybridization. Now, this theory of hybridization was put forward by Linus Pauling, who is the same person who came up with the electronegativity values that we use in this course. And basically, this problem came about, well, the theory came about because there was a problem explaining certain bonding situations. And I'm going to use carbon as an example. So what we have here is the electronic configuration of carbon. This here is the electronic configuration of carbon. And you'll notice that in the valence shell of carbon, you have 4 electrons, right? But 2 of them are paired and 2 of them are unpaired in the two of the 3p orbitals, all right? Now, based on what we have discussed before, one would expect that if carbon were to combine with, let's say, with hydrogen, all right? Then because you have 2 unpaired electrons here and here, then you'd expect that carbon would only form 2 bonds with hydrogen. But we know that's not the case because we know that the formula for methane is CH4. So the question now becomes, how is it that carbon is able to form 4 bonds with 4 hydrogen atoms? Well, according to Linus Pauling, this happens because what happens before the bonding takes place is that one of the 2s electrons will be promoted to the vacant 2p orbital, right? So this electron here will be promoted here by the acquisition of energy from the environment. So you're going to end up with 4 unpaired electrons in the valence shell. And that helps in terms of making a step towards explaining this. But there's another problem with this as it is. And the problem is that the s orbitals, as we all know, has a spherical shape like this. And the p orbitals, they have a shape which is more like this. So one would expect that if carbon were to bond with 4 hydrogen atoms, then basically the lengths of the bonds will be different because the s orbitals have a circle shape. So therefore you'd expect that that carbon to hydrogen bond would be shorter, and the p orbitals, which are more extended, you'd expect that the bonds formed from those p orbitals would be longer. In other words, it would not be a perfect tetrahedron, which we know is the shape of the methane molecule. So there's another step that is involved in this idea, and this is where the actual hybridization concept comes in. Basically, what will happen is that these 4 orbitals will be mixed, or the term that is used is hybridized, to form these separate orbitals, and these orbitals are called sp3 hybrid orbitals, right? And they're called sp3 because they're formed from an s orbital and 3 p orbitals. So this s orbital will mix with these 3 p orbitals to form 4 sp3 hybrid orbitals. And these hybrid orbitals now have the same shape, and therefore when they overlap with the 1s orbital, the bonds between the carbon and the hydrogens will be the same. So that is how the hybridization theory is used to explain the structure of molecules such as CH4, methane. So just to give you a picture of what we're talking about here, these are the 3 p orbitals of higher energy compared to the s orbital here, which will be low in energy. And when this s orbital combines with these 3 p orbitals, you're going to end up with the 4 sp3 hybrid orbitals, and the energies of these 4 sp3 hybrid orbitals would be the same, somewhere in between those of the p and the s orbitals. And you'll notice that the way the sp3 hybrid orbitals are arranged, they're arranged in a 3-dimensional way in the form of a tetrahedron, right? And this explains in further detail why the methane molecule is a tetrahedral molecule, because what will happen, in fact, let me see if I have it here. Hold on. Okay, so here it is. So when the sp3 hybrid orbitals overlap here, 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 and here, you're going to end up with the structure of the methane resulting. So you have a bond here, a bond here, bond here, bond here, and this is a tetrahedral arrangement. And that's basically how the hybridization theory is used to explain the structure of methane in this case, all right? And this is true not only for methane, but true for other molecules as well that has this sort of arrangement. Okay, any questions concerning sp3 hybridization? Any questions? Any questions? Okay, so we see a similar situation in the case of ammonia. Now, in the case of ammonia, you have nitrogen, and let me just draw the electron in box representation of nitrogen here. So here we have the electron configuration of helium. Then we have the 1s orbital, I'm sorry, 2s orbital, which has 2 electrons. And then we have the 3 2p orbitals, which will have 1, 2, 3, and then 4th one would go here. So these are the 2p orbitals, right? So what's going to happen is that the 2s orbital will mix with the 2p orbitals, and you're going to end up with 4 sp3 hybrid orbitals. 2 electrons will be one of them, and the others will be singly occupied. And these will overlap with the hydrogens, as you can see here, here, here. So these orbitals here will overlap with the hydrogen, overlap with the hydrogens. And this 2p, this sp3 hybrid orbital here would be this one right here with the 2 lone pairs of electrons, all right? So these are the sp3 hybrid orbitals that will be formed as a result of the mixing or blending or hybridization of the 2s and the 2p orbitals. So that's basically how that works in the case of ammonia. Okay, then we have another type of hybridization, which is called sp2 hybridization. And in that case, what happens, as the name suggests, is that one 2s orbital will overlap with 2 of the 2p orbitals to form a set of 3 sp2 orbitals. Now, this here is the electron configuration of 2, 4, 5. That's boron, I think. All right. And in this case, you'll notice that you have 2 electrons here in the 2s orbital, 1 electron here in the 2p orbital. So first thing that would happen is that this electron here will be promoted to one of the 2 vacant p orbitals here. And you end up with this situation. And then you're going to have the hybridization of these hybrid orbitals here. And this one would be unaffected by hybridization, unaffected by the hybridization process. And you're going to end up with this situation here, where now you're going to have 3 sp2 orbitals, hybrid orbitals, that are singly occupied, and you're going to have a vacant 2p orbital here, all right? And in terms of the picture that, hold on, let me see here. Okay, so the picture that develops is that these are your 2p orbitals that will undergo hybridization, and this would be your s orbital, which is going to be mixing with these 2p orbitals, and you're going to end up with your 3 sp2 hybrid orbitals. And you'll notice that the way they are arranged is in a trigonal planar arrangement, all right? Where the angle here and here would be 120 degrees. Here you're going to have your unaffected p orbital, will maintain the same shape as before, right? So same shape. The shape would be the same. And that's basically what happens in the case of sp2 hybridization. So this happens, for example, in the case of a molecule like boron trichloride. And that's the reason why the boron trichloride molecule is a trigonal planar shape, all right? Bond angle here will be 120 degrees. Okay, so let's move on now to the other form of hybridization known as sp hybridization. And in this case here, you have the blending of an s orbital with 1 p orbital. Let me see here, so we're talking about an element which would have this configuration, I'm sorry. 2s2 and 2p. Yeah, I think that's it. Which would be hydrogen, beryllium, right? So this is electronic configuration of beryllium. In fact, in terms of the boxes, you're going to have 2 electrons here, no electron in any of the p orbitals. And then 1 electron here will be promoted here. So, and then you're going to have the hybridization with the s and p to get 2 sp orbitals and 2 p orbitals that are unaffected. I'm sorry, this should be. Okay, so, right. So these are your 2p orbitals. And what's going to happen is that you're going to have the sp orbitals having 2 electrons, as you can see here, 1 in each sp orbital. And the 2p orbital will be unaffected by hybridization, unaffected. And you'll notice here that the way the p orbitals are aligned is like this, linear arrangement. So a good example of a molecule that will display the shape would be beryllium chloride or beryllium dichloride, where the shape is linear. The bond angle here would be 180 degrees. All right, so those are different types of hybridization, which accounts for the shapes of different molecules. Then you have some further hybridization that can take place where d orbitals are involved. Now, this would happen when it comes to elements in the 3rd period and below or beyond. And this one here is for phosphorus. What you're looking at here is the electronic configuration for phosphorus. And you'll notice you have a paired electrons in the 3s orbital. The 3p orbitals would be singly occupied. And you have the d orbitals here, which are close by in terms of energy. And what will happen is that this electron here will be promoted to this orbital here, and you end up with each of these orbitals being singly occupied, including this 1 3d orbital here. And then you're going to have hybridization taking place between the 3s, the 3p, and one of the 3d orbitals, right? So we call this sp3d hybridization. These 3d orbitals here will remain unaffected by hybridization like this. And you'll notice that the arrangement of these 5 sp3d orbitals would be the trigonal bipyramidal arrangement that is shown here, all right? So a good example of a molecule that displays this sort of arrangement, this sort of hybridization would be phosphorus pentachloride, which would have this structure here. Cl here, and then a Cl up here. This would be the trigonal bipyramid structure or shape of the phosphorus trichloride pentachloride molecule, all right? Okay, so that's what happens in the case of sp3d hybridization. And let me just say something here. If you remember, I said that when it comes to drawing the Lewis structures of molecules, there are some atoms that can expand its octet beyond 8 in order for bonds to be formed. And if you remember, I said that those atoms will be found in period 3 and beyond. And this is the reason why, because in the case of those elements, there are d orbitals which would allow for single electrons from a lower orbital to go into so that they can become unpaired, so that you can increase the number of unpaired electrons so that you can have more than 8 electrons in the end when you have bond sharing or electron sharing taking place to form a bond in each case, right? So that's why elements like phosphorus and sulfur and elements beyond period 3 can display this sort of situation where the phosphorus can end up with more than 8 electrons on its outer shell. And that's because of the more easily accessible d orbitals that will be present in those shells. In the case of elements in periods 2, the electrons in the valence shells would not have access to any d orbitals, and therefore they cannot expand their octets. Okay, and then the final type of hybridization we're going to look at is in the case of something like sulfur, where you have this situation here in the valence shell, where you have 2 electrons here in the 3s orbital, you have 4 electrons here in the 3p orbitals. So therefore, you can have unpairing of this and this taking place, where this electron is promoted here, that electron is promoted to another d orbital. So now you're going to end up with 6 unpaired electrons, which can pair up with 6 other electrons from other atoms. But of course, hybridization would have to take place before. And in this case, you're going to have the mixing of the 3s with the 3p with 2 of the 3d orbitals to form a total of 6 hybrid orbitals. And of course, the type of hybridization here is sp3d2. These 3d orbitals would be unaffected by hybridization. And this would be the spatial arrangement or the shape that would result, an octahedral shape that would result as a result of that type of hybridization, all right? And we can go beyond this, but of course, at our level, we will just stop here, right? We won't go beyond a situation where we won't go beyond sp3d2 hybridization. Now, you might realize, or you might pick up on the fact that there is some correlation between the hybridization and the shape of the molecule, right? And there's a table I'm about to show you, but before we do that, let me just say, how do we predict the type of hybridization? First, we have to draw the Lewis structure. Then we have to determine the shape of the molecule using the VSEPR theory. And then we select the hybridization that correspond to the shape that is predicted by the VSEPR theory. And of course, you can describe the orbital overlap and molecular geometry if asked. So this table here basically summarizes the correspondence of the shape of the molecule and the hybridization for the central atom in that molecule. So if the hybridization is sp, then the orientation of the electron group geometry would be linear. If it's sp2, then it's trigonal planar. If it's sp3, then the orientation will be tetrahedral. If it's sp3d, then it's trigonal bipyramidal. And then if it's sp3d2, it would be octahedral. And these are just some examples of molecules, the corresponding molecules with the shapes and the hybridization. Okay, so that's basically what hybridization is all about. Now, what we're going to look at now is some other applications when it comes to organic molecules. But before we do that, I promised you that there are two types of bonding when it comes to covalent bonds. We have sigma bonds, which is one that we were talking about before, where we have the end-to-end overlap of orbitals, right? And it doesn't matter what type of orbitals, it could be s, p, d, f orbitals, but those are sigma bonds, right? Resulting. Every single bond that you see in any molecule are single bonds, all right? So that's one thing we can say about single bonds. They're all sigma bonds. In other words, they're all formed as a result of the type of overlap that I described here, end-to-end overlap of orbitals. Now, if you have a side-by-side overlap or parallel overlap of orbitals, then we call that orbital a pi orbital, right? And one can see that happening in the case of p orbitals overlapping. We're going to see some examples of that shortly. Now, if you have a double bond that is present in a molecule, then what you'll find is that one of those bonds would be a sigma bond, which is formed as described up here, and the other one would be a pi bond, which is formed, as I said before, as a result of parallel overlap. And then in the case of a triple bond, it is made up of one sigma and two pi bonds, right? So the sigma bond here again is formed as a result of an end-to-end overlap, and the two pi bonds are formed as a result of a parallel overlap of two sets of p orbitals. And I think the next slide will show us a picture of what we're talking about here. Now, what this is showing you here is the framework for the molecule ethene. Let me draw the Lewis structure of ethene over here. It is C, double bond C, H, H, H here, and H here, all right? Now, as far as the carbon to hydrogen bonds are concerned, these are all sigma bonds. These are all formed as a result of an overlap of an sp3 orbital, excuse me, with a 1s orbital, right? So these are all sigma bonds. And there's also a sigma bond formed between this carbon here and this carbon here. And this overlap is the result of this sp3 orbital overlapping with this sp3 orbital, sp3 orbital, all right? So basically, we call this the sigma framework, right? It shows you basically all the sigma bonds within this molecule. Now remember, for an I'm sorry, I misspoke. This is not sp3, this is sp2. The carbons are sp2 hybridized, my bad. All right, and the reason why I just picked up on that is because there's a vacant, or I should say unaffected p orbital that is present on each carbon as well, all right? So what's going to happen is that you're going to have the sideways overlap of these p orbitals here and here, right? And that will result in the pi bond that we're talking about here, all right? So basically, the double bond here between the two carbon atoms here, one of them would be the sigma bond, which we talked about here, as a result of the overlap of sp2 hybrid orbitals here and here. And then the pi bond would be formed as a result of the lateral or sideways overlap of p orbitals, which gives you the pi bond, which is what this is, all right? So this basically summarizes all the different types of bonds that would be found in ethene, right? One bond here would be a pi bond formed as a result of the overlap of two p orbitals from either carbon. The other bond would be a sigma bond resulting from the overlap of sp2 hybrid orbitals, and then all the other carbon to hydrogen bonds would be as a result of the overlap of the 1s orbital of the hydrogens with the sp2 hybrid orbital of each carbon atom occurring, all right? Okay, I'm going to take a break here. It's now 9:49, and then I'm going to pick up on sp hybridization and the type of bonding that would take place in a carbon-to-carbon triple bond. All right, so I'll be back at 11. I'm sorry, 10 o'clock. Okay, folks, I'm back. So I'm going to continue to discussing the bonding situation in the next molecule, which is ethine. Okay, so we're talking about, let me do this here. Okay, so we're talking about this molecule right here. Oh, shoot. What's going on here? What's going on here? We're talking about this molecule right here. And in this case here, the carbons are sp hybridized. So this is sp hybridized as well as this one, which means that it has two sp orbitals. So for this carbon, these are the two sp orbitals here and here. Same thing on the other side here. And you have a sigma bond formed between the sp orbitals here, and a sigma bond formed between this carbon and this hydrogen, and the same thing on this side here, this carbon and that hydrogen. So this is a sigma framework. And then now, and this is a bit more challenging to see, but bear with me. For each carbon atom, there are two p orbitals. One of them, for example, for this carbon, one of them is this one right here. I'm drawing a line right through it. And the other one is perpendicular to it, like this. And you have another p orbital on the other carbon, like this, a line like that. And then the other p orbital will be like this. So these two p orbitals that are parallel to each other, these two here, that are parallel to each other will overlap like that. And the other two p orbitals, namely this one and this one, will overlap sideways, and then it's kind of hard to see on the other side, but like that, all right? So the result would be the formation of two pi bonds, right? So you have two pi bonds being formed as well as a sigma bond being formed between the two carbon atoms, right? So over here, they summarize what's happening here. There are two pi bonds formed as a result of the sideways overlap of two p orbitals. And then there's a sigma bond, which is formed as a result of the lateral overlap or end-on-end overlap of sp orbitals. And then finally, the carbon to hydrogen bonds are the result of overlapping of an sp and a 1s orbital. In each case, same thing is true here and here, right? So when it comes to organic molecules, these are the type of bonds that you have to be aware of. And just to summarize, if you have a single bond, all single bonds are sigma bonds. So single bonds are made up of just sigma bonds. Double bonds will be made up of one sigma and one pi bond. And then triple bonds are made up of one sigma bond and two pi bonds. So that's basically a summary of the bonding situations when it comes to organic molecules, carbon to carbon, single, double, and triple bonds. Okay, now one of the consequences of this arrangement when it comes to specifically carbon to carbon double bond is a phenomenon known as geometric isomerism. Now, isomerism, again, this will be very important for those of you who plan to do organic chemistry, but basically isomerism is the existence of two or more compounds with the same molecular formula, right? That's what isomerism is. And you have different types of isomerism. The one that we're going to talk about here is geometric isomerism. And that is seen, for example, when you look at these two compounds, right? And because of the overlap situation, now remember, there's a pi bond here. The pi bond overlap is sideways, right? Because of the overlap situation and the pi bonding situation here, the resulting structure here is rigid, right? So therefore, you have the existence of two possible compounds where you have carbon atoms bonded to each other through a double bond and each bonded to a hydrogen and a CH3 group, right? So this particular form of this molecule is called cis-2-butene. You don't need to know about the rules for naming these compounds here. And this one is called trans-2-butene because in this case here, the two hydrogens are on the same side of the molecule, whereas in this case here, the two hydrogens are on the opposite side. So the one with the same side is called the cis isomer, and the one where the hydrogens are on the opposite side are called the trans isomer, all right? So this exists in organic molecules, all right? And it's as a result, as I said before, of the pi bonding overlap that occurs between these two carbon atoms here, which are sp2 hybridized, all right? So that's one consequence of pi bonding. Now, very important for you to realize that these are two completely different compounds, right? Even though their composition is the same, and even though the way the atoms are bonded to each other are the same, but by virtue of the fact that there's a different spatial arrangement, these two atoms are different. They have different boiling points, different melting points, different refractive indices, and even behave chemically in different ways, all right? So that's basically what happens in the case of the geometric isomerism of cis and trans 2-butene. Okay, the next thing I want to talk about here is molecular orbitals. Now, this is another approach to understanding bonding in, well, covalent bonding, basically. And this is a purely mathematical approach, which explains a lot of things that we would observe with respect to these types of bonds, right? So the molecular orbitals that we're going to be discussing are mathematical equations that describe the regions in a molecule where there's a high probability of finding an electron, right? So if you remember when we talked about atomic orbitals, which is the region in a molecule, or I should say a region in an atom, where there's a high probability of finding an electron. Well, the same kind of terminology applies when it comes to molecular orbitals. It's a region in a molecule where there's a high probability of finding an electron. And there are two types of molecular orbitals. You have what are known as bonding and anti-bonding molecular orbitals. And we're going to see how those are created. Molecular orbitals are built up in pretty much the same way as atomic orbitals. And this is in reference to how the electrons are distributed among molecular orbitals. It's basically following the same rules as in the case of atomic orbitals. Okay, so just to give you an example, starting with hydrogen, simplest example, we know that hydrogen is a diatomic molecule consisting of two atoms, and each atom, in order for the bond to form, must have an electron in its 1s orbital spinning in opposite directions. So this is one hydrogen atom, this is the other, and as you can see here, the 1s orbitals are spinning in opposite directions. So according to the molecular orbital theory, when these orbitals overlap, they create two orbitals, right? The bonding molecular orbital, which would be of a lower energy compared to the atomic orbitals, and then we have the anti-bonding molecular orbital, which is of a higher energy and therefore less stable compared to the 1s orbitals, right? So first thing I want to point out here is that whatever the number of orbitals that are combined here in terms of the atomic orbitals, the number of molecular orbitals are the same. So therefore, we can say that orbitals are not created nor destroyed. Whatever the number of atomic orbitals that you start off with here, you must end up with the same number of molecular orbitals. And then it becomes a question of where the electrons will end up. These electrons that were previously in the atomic orbitals, where will they end up? And the answer is they will both basically go into the bonding molecular orbital in the ground state, right? So one electron will go here, and then the next electron will pair up with it, spinning in the opposite direction. And that would basically be the electron configuration for hydrogen, the molecule, as opposed to hydrogen, the atom, all right? So this would be the ground state configuration. And of course, you can have an excited state where one of these electrons, let's say this one, is promoted to the anti-bonding molecular orbital formed from the 1s orbitals. And that electron would be here, all right? But that would not be a ground state configuration. That would be an excited state configuration, all right? Now, the difference, how should I put this? The physical difference between bonding and non-bonding or anti-bonding molecular orbitals is that the anti-bonding molecular orbitals is a region of diminished electron density. So the electron density that one would observe here in the case of the anti-bonding molecular orbital is diminished. And therefore, as a result, the nuclei of the two atoms will be more exposed to each other, and therefore there will be a repulsive force. And therefore, the energy of this orbital here is higher because this represents an unstable state, all right? In the case of the bonding molecular orbital, the region of that orbital between the two nuclei would be of a relatively high electron density, and therefore there will be a strong attraction between the nucleus and the shared electrons, and therefore this would be more stable compared to the 1s orbitals from which they're formed. Okay, we can also have the same sort of situation, molecular orbitals formed from p orbitals. So for example, if you have two p orbitals overlapping end on n, then you have the bonding molecular orbital here from the two p orbitals and the anti-bonding sigma molecular orbital. So these are both sigma, but one is bonding and one is anti-bonding. Now, if you have the sideways overlap, you're going to have the pi bonding resulting here and here, and the same thing is true here. So these are the different orientations, the pz and the py orbitals, and their corresponding anti-bonding orbitals and bonding orbitals, right? So again, you'll notice that if you start off with two orbitals that are atomic, then the resulting molecular orbitals must be two of them, all right? Again, orbitals cannot be created nor destroyed. Okay, so we can represent what we just talked about in the form of a molecular orbital diagram. So this is the molecular orbital diagram for the H2 plus ion, right? So basically what is happening is that this hydrogen atom here with one electron is combining with a hydrogen ion, right? And this is what happens. You're going to have the sigma bonding and sigma anti-bonding orbital, but there's only one electron that is shared between both of them. And that electron will go into the 1s orbital. So this would be the molecular orbital diagram for the H2 plus ion, all right? So let me see here. Well, I mentioned this before. The antibonding molecular orbitals are high in energy, and the molecular the bonding molecular orbitals would be lower in energy, which in this case would be the sigma 1s orbital formed from the 1s orbitals of the different hydrogen atoms. Okay, so if you look at the molecular orbital diagrams of different elements, you'll see something like this. Now, what this actually represents would be the molecular orbital diagrams for elements in period 2, starting from lithium and ending with neon, all right? And what you'll see is that there's a certain order of energy with respect to the molecular orbitals that are formed. So in the case of the lithium diatomic molecule, right, when two lithium atoms come together to form one molecule, in the valence shell, there's only one electron in the 2s orbital. So when you have the overlap of the 2s orbitals from each of the atoms, you're going to have the formation of the sigma 2s bonding and anti-bonding orbitals, and you have the others as well as a result of the overlap of other orbitals. However, there are only two electrons present in the case of the lithium molecule, and those two electrons will simply go into the lowest orbital or orbital of lowest energy, and that would be the sigma 2s orbital. So basically this would be the electron configuration of the lithium molecule. In the case of the beryllium molecule, well, you're going to have two electrons in the bonding orbital here, sigma, and then the sigma anti-bonding orbital here, and that would be the electron configuration of the beryllium molecule. And then when you get to the boron molecule, what will happen is that after these two orbitals are filled, when you get to the pi 2p orbitals, each of them will be singly occupied. If you remember when we were talking about the electron configuration of atoms, whenever you have orbitals of equal energy, then the electrons will occupy them singly before pairing up, all right? And then when you get from boron to carbon, then you have the pairing taking place, and then this level is completely filled. And then when you get to nitrogen, the next two electrons will go into the next higher orbital, which would be the sigma 2p orbital. Now, let me just say something here. Something kind of weird happens as you go from nitrogen to oxygen. What you'll find is that as you go from nitrogen to oxygen, the energies of the sigma 2p and the pi 2p take each other's place, or they flip. So basically what's going to happen is that as you go from nitrogen, as you go from nitrogen to oxygen, this orbital here will come down here, and this set of pi 2p orbitals, will go up here, and you end up with this arrangement, all right? So please make a note of that as you go from nitrogen to oxygen, that's what happens, right? In any case, in the case of oxygen, the next 2 electrons will go into the pi anti-bonding 2p orbitals, all right? And then the next two electrons, as you go from oxygen to fluorine, will will pair up with these 2 electrons here. So you end up with this. And then finally, in the case of the neon molecule, you're going to end up with the 2 electrons occupying the sigma anti-bonding orbitals formed from 2p atomic orbitals, all right? So that's basically what happens as you go from lithium to nitrogen, from lithium to neon, with respect to the electron configurations of the diatomic molecules of those elements. Now, if you remember, we talked about paramagnetism earlier. I forgot what chapter it was. I think it was chapter 8. We talked about paramagnetism. And remember, we said that a substance will display paramagnetism when there are unpaired electrons in its molecule, all right? Well, this is where we see why oxygen, if you remember the video, in fact, let me show you the video again. Let me keep this, where they use 2 liquids, liquid oxygen and liquid nitrogen, and it is oxygen that display the phenomenon of paramagnetism. So let me go here. Let me, hold on 1 minute.
Gold Cush, no baloney.
Just science. Hi, I'm Joanna.
And I'm Steve.
And this is a test tube of liquid nitrogen.
And this is a test tube of liquid oxygen.
Let's see what happens when we pour the liquids past the poles of a strong magnet.
Okay.
Now, liquid nitrogen isn't normally magnetic, but each of the nitrogen molecules acts like a tiny magnet when it's exposed to a magnetic field. This effect is known as diamagnetism. That's just a fancy way of saying that each of the nitrogen molecules is repelled by the magnet's magnetic field. So when I pour the liquid nitrogen past the magnet's poles, it doesn't look like anything special happens. The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
Just like nitrogen, oxygen isn't normally magnetic. And just like nitrogen, each molecule of oxygen behaves like a tiny magnet when it's exposed to a magnet's magnetic field. Oxygen behaves differently than nitrogen, though. The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
Thanks for watching. I hope you'll join us again soon for another experiment.
Let's try that with liquid nitrogen at the same time.
Okay.
Okay, let me stop that right there. So basically the result of that little experiment, let me go back to this here. Okay, so basically the result of that experiment is that oxygen is paramagnetic and nitrogen is not. And we can see the reason why based on the molecular orbital diagram in the case of nitrogen compared to oxygen. Because in the case of oxygen, you'll notice that there are 2 unpaired electrons here, right? So this is responsible for the paramagnetism of oxygen because of the unpaired electrons present, right? Each pi orbital here is occupied by a single electron. In the case of nitrogen, if you look at the electron configuration here, you'll see that there are no unpaired electrons. So therefore, nitrogen does not display paramagnetism. All right. So that's one consequence of looking at what happens here with respect to the electron distribution among the molecular orbitals in diatomic molecules. Okay. Any questions about this? Any questions? Any questions? Okay, so we can apply what we have talked about in terms of hybridization and so on in the molecule of benzene. Just a few comments here about benzene. The structure of benzene was discovered by Kekulé, and there's an interesting story about this because even though it was discovered by Michael Faraday in 1825, it took a long time, relatively speaking, for the structure of benzene to be determined in 1865 by Kekulé. And Kekulé claims that the idea for the structure of benzene came to him in a dream. I don't know how true that is, and there are a lot of people who doubt that to be the case. In any case, he came up with this cyclic structure representing benzene, all right? And if you look at the structure, you see that there's an alternating double, single, double bond around the ring, all right, with each carbon bonded to a hydrogen. This structure is not actually a true structure representing benzene because we now know several things about benzene which contradicts its structure. For one, we know that all the bonds within the between the carbons are of the same length. If this structure was true, then the carbon-to-carbon double bond would be shorter compared to the carbon-to-carbon single bond. In other words, the shape of the benzene molecule is expected to be something like a distorted hexagon. But we now know that it's actually a perfect hexagon right around. So therefore, we know that this structure here is one resonance structure of two resonance structures. And therefore, the hybrid structure would be a combination of those two resonance structures, which I won't get into right now. Suffice to say, the idea of resonance, well, okay, so here are the two resonance structures, right? I mentioned earlier. The hybrid structure is, of course, a mix between these two. And in some textbooks, they use a circle instead of the bonds to represent the fact that these electrons here are moving around. In other words, they're delocalized. That's a term that we use around the 6 carbon atoms. So that would be the hybrid structure, and these would be the resonance structure. Now, in terms of the actual bonding that takes place within this molecule, each carbon atom is sp2 hybridized, and therefore what you'll have is that each carbon-to-carbon bond is an sp3 overlapping with an sp3, resulting in a sigma bond. So all these bonds here between the carbon atoms are sigma bonds. Sigma, 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 and sigma. All right? And the same is true for the carbon to hydrogen bonds. These are all sigma bonds here, 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 and here. Now, what is not shown here is where the pi bonds are formed as a result of the overlap of the p orbitals. So I'm going to try to draw this on this diagram. And please forgive me of my lack of artistic skills. We have one p orbital here. On this carbon, you have another p orbital here, another p orbital here, and then going around the ring, you have another one here, another one here, and the 6th one is here, all right? And then what's going to happen is that the p orbitals will overlap above and below the plane of the sigma framework. So one overlap will occur here, another will overlap here, same thing down here, and then here, and here, and then here, and here, and then here, and here, right? So that would be the pi framework, so to speak, where you have the overlap of the p orbitals, right? And then the result of that would be basically a ring, the pi orbital, which is what this represents. So you're going to have a pi overlap here. The pi overlap will be right around the ring, right? And therefore we say that the electrons are delocalized around the ring, all right? So what that means is that the electron that would have been here in the p orbital, when the overlap takes place, that electron would not belong to this carbon atom, but basically belong to all the carbon atoms in the ring. All right, so that's where we use the term delocalized pi system to describe the situation occurring here. Okay, so much for that. So this is just some general information about organic aromatic compounds. Again, for those of you who have to do organic chemistry, you'll be meeting this sort of situation. Initially, these were called aromatic compounds because they have, a lot of them, not all of them, have pleasant odors, even though some of them are toxic, and therefore they're described as aromatic. But in chemistry, we now refer to systems with delocalized pi system as being aromatic, all right? So that's the chemistry definition, right, of aromatic compounds. Aromatic compounds are compounds that have a delocalized system of pi electrons within its ring structure. Okay, all right, so that's basically it for chapter 10. So what I'm going to do now is move on to chapter 11, which is the last chapter in this course. Let me scroll back up here. I was reviewing it this morning. Okay, so in chapter 11, we'll be looking at matter, the states of matter, and the type of intermolecular forces, and I should add ionic forces as well, that exist in different substances, all right? So that's basically the focus of this chapter. So when it comes to molecular compounds, you can have what are known as intramolecular forces, which are the forces that exist between the molecules, and then, well, actually within an atom, I should say, or within a molecule. And then you have intermolecular forces, which are the forces that exist between molecules. So for example, in the case of water, right, if you look within the molecule, there are different forces. Actually, you have the covalent force that exists between the oxygen and hydrogen atom, right? That's a bond. And that would be referred to as an intermolecular force because that's a force that exists within a molecule. And then we have what are known as intramolecular forces, which are forces that exist between molecules, such as the force that exists between the hydrogen atom of this water molecule and the oxygen atom of another molecule, all right? So that force is called an intermolecular force, right? And the thing about intermolecular forces is that they impart certain properties to substances. For example, intermolecular forces can be used to predict, to some degree, tendencies in terms of boiling points, melting points, and other properties, which we'll get into, all right? Okay, so we talked about gases before. We know the nature of gases. We know the reason why gases behave the way they do. We know that gases, their particles move in straight line unless they collide with each other. And, you know, they're always in rapid motion. Essentially, for the most part, they're independent of each other in terms of intermolecular forces, but the same is not true for liquids, right? Liquids are on average closer to each other. They're not as energetic, and there are strong forces, relatively speaking, that holds the particles of a liquid together, right? So there are significant differences between the way gases behave and the way liquids behave based on what I just described. Gases, they tend to fill the container that they're in, where liquids will have a fixed volume and assume the shape of the container. Okay, and then when we get to solids, the forces are even stronger. They're less energetic, the particles that is, and therefore they have fixed volume, definite shape, and generally less compressible than liquids. And in terms of the motion of the particles, they don't move around like in the case of liquids and gases. In fact, their motion is more or mainly vibrational, all right, around a particular equilibrium point. So this is just basically a summary of the different states and the type of intermolecular forces that exist between the particles in the different states. Okay, so let's talk about this term, vaporization. What is vaporization? Vaporization, of course, is a conversion of a liquid to a gas, right? So we're talking about the molecules escaping the liquid state and moving into the gaseous state. And as you can imagine, that requires energy. And in fact, we have what is known as the enthalpy of vaporization, delta H V or VAP, which is the amount of heat that must be absorbed to vaporize a given amount of liquid at a constant temperature. So for example, in the case of water, to convert H2O liquid to H2O vapor, the amount of heat needed is 44 kilojoules per mole. And of course, it's positive. You'd expect that because of course, energy is required and therefore that process would be an endothermic process, all right? So that's what enthalpy of vaporization is all about. And then we have the reverse of that, which is condensation, which of course corresponds to the enthalpy change when you have the gas converting to a liquid. The enthalpy for that would be, of course, negative, whatever the enthalpy of vaporization is. So for example, in the case of H2O gas converted to H2O liquid, the enthalpy of condensation would be minus 44 kilojoules per mole. And that, of course, is what you'd expect. Okay, so that's condensation and vaporization. And of course, enthalpy being a state function, that means that the enthalpy change of vaporization or condensation would be a state function as well. And you have different values for different substances. As you can see, water is relatively high. Ethanol is very close to it. Aniline is the highest of these in this list right here. But these are just some examples of different compounds. And what you're going to see is that the magnitude of this term, enthalpy of vaporization, is related to the type of intermolecular forces that exist between the molecules, all right? Another thing we need to talk about here is vapor pressure. What is vapor pressure? It is the partial pressure exerted by a vapor when it is in dynamic equilibrium with a liquid at constant temperature. So to demonstrate what we're talking about here, let's say we have a liquid in this beaker right here, and we cover that with a jar, all right? So no vapor can escape from outside the jar. So initially, you're going to have some molecules escaping from the liquid state into the vapor state, and that will continue until you get more molecules present here. At the same time, you're going to have some molecules leaving the vapor state and going back to the liquid state. So you're going to have this back and forth taking place. You're going to have vaporization taking place, and then you're going to have condensation taking place. And that will continue until you reach an equilibrium point where the rate of vaporization will be equal to the rate of condensation. So initially, the rate of vaporization will be greater than the rate of condensation, all right? So at that point, you're going to have more molecules entering the vapor state compared to molecules entering into the liquid state. But when you get to a point here where the vaporization rate is equal to the condensation rate, then basically you achieve what is called a state of dynamic equilibrium, all right? Now, this is assuming, all that I've described here is assuming that the temperature is constant, right? Now, if I were to take this and increase the temperature of the liquid inside here, then what will happen is that more molecules will enter the vapor state, and then you're going to achieve a new state of dynamic equilibrium, all right? So basically, the dynamic equilibrium state will be achieved when temperature is constant, when the temperature is constant. If you change the temperature, then basically more molecules would enter into the vapor state, and you're going to achieve a new dynamic equilibrium state. And at that point, the vapor pressure would be higher compared to the vapor pressure that, that was in existence before you increase the temperature. Okay, so the vapor pressure is temperature dependent, and that can be seen in this table here when we look at the vapor pressure of water. So as you can see in this table, we have the temperature and the corresponding vapor pressure of water. And you can see clearly as the temperature increases, the vapor pressure increases, right? And that is true for every single liquid without any exception, right? When you increase the temperature, the vapor pressure of the liquid increases. And I think the next slide has a graph. Yes, it does. And this shows you for different substances, whoops, sorry. This shows you for different substances a plot of vapor pressure versus temperature. Now, if I'm not mistaken, the blue line here labeled D, that is the curve for water. The others, to be perfectly honest, I don't know what they are. So in any case, in the case of water, as you can see, the vapor pressure increases as the temperature increases. The same is true for C, B, and A. And the immediate thing I can say about these three liquids here is that, let me see here, is at the same temperature, water would have the lowest vapor pressure, right? So for example, if you take 40 degrees here, right, as a temperature, and you compare the vapor pressures of the different liquids, you'll see that water has a vapor pressure of about, I would estimate that to be about 50 or just about 50, maybe 60 millimeters mercury. And then in the case of C, whatever C is, its vapor pressure would be about maybe just under 150. And then in the case of B, its vapor pressure would be about 250. And then in the case of C, its vapor pressure would be about 600 millimeters mercury, all right? So basically, the term that we use to describe liquids with high vapor pressure, we say that they are volatile. So volatile refers to, how should I put this? Refers to how high the vapor pressure is for a liquid. All right. So basically, we can say that A is more volatile than B, which is more volatile than C, which is more volatile than D in terms of volatility. Volatility. All right. And that's because A has the highest vapor pressure for the same temperature compared to the others, and then B follows suit, then C, then D. All right. Okay. So that's basically what we can say about the vapor pressure as a function of temperature. Okay, another definition here we need to talk about, boiling point. Definition of a boiling point is it is the temperature at which the vapor pressure becomes equal to the external pressure, right? So it's not just simply the temperature at which water boils, it's the temperature at which the vapor pressure of the liquid becomes equal to the external pressure. So for example, the normal boiling point of water is 100 degrees Celsius because that is the temperature at which the vapor pressure of water is equal to the external pressure, which would be the atmospheric pressure, right? So when the external pressure is 1 atm, 1 atmosphere, the boiling point is 100 degrees Celsius. Now, if you reduce the pressure, then there will be a corresponding reduction in the boiling point of the liquid, all right? So if you take water and reduce the pressure, the external pressure, so you put it in an environment where the pressure is less than 1 atmosphere, then the boiling point of the water under those conditions would be less than 100 degrees Celsius. Let me see here. Okay, so let's talk about, no, this, I think this slide is, it's not in the correct order. I'm sorry about this, folks. Let me just check something here. Okay, I'm going to, let me see here. I'm going to talk about the melting point first before I talk about the phase diagram. Yes, something is wrong here. This is not in the correct order. I'm sorry about this, folks. I'm going to, after this class, I'm going to change up the directions or the order of, all right. Let me scroll down to melting points. Okay, so when it comes to phase changes with respect to solids, right? I'm quite sure we're familiar with the process of melting, right? Where we have the conversion of the solid to a liquid state, right? So that is called melting, or we can call it fusion. And the temperature at which you have the equilibrium between the solid and the liquid state is the melting point. So let me put that there, what I just said here. The melting point, which is the temperature at which there is an equilibrium between solid and liquid. All right, that's the actual definition of the melting point. The melting point is a temperature which is an equilibrium state between the solid and the liquid state. All right, and at the melting point, of course, energy is needed, and the enthalpy of fusion is the amount of heat needed to melt a given amount of solid, right? And I think there is a table, let me see here. Right, so there's a table here which gives you the enthalpy of fusion of different substances along with their melting point. So for example, in the case of water, the melting point is 0.0 degrees, and the enthalpy of fusion is 6.01 kilojoules per mole, all right? And we have the values for other substances. Okay, another term that you need to be familiar with is sublimation, right? Sublimation is what takes place when the solid is converted directly to a gaseous state, right? I don't know how many of you are familiar with dry ice, but dry ice is basically frozen carbon dioxide, right? And if you have any experience with dry ice, you'll know that if I took a piece of dry ice and put it on a table, let's say, or put it in a beaker and leave it exposed to the atmosphere, then what will happen is that the mass of the dry ice will shrink and you'll see some fumes emanating from it. And the fumes emanating would be carbon dioxide, because what is happening is that the carbon dioxide solid is being converted to carbon dioxide gas, all right? So that's what happens in sublimation, right? You're having a direct conversion of the solid state to the gaseous state. Here's another example of sublimation. What you see in this picture right here. What you see in this picture right here is iodine. Let me write it down here, in a solid state. And again, if you leave it at room temperature conditions, then what will happen is that the iodine solid will be converted to iodine gas, all right? And that is what is seen in this here. Iodine is a purple solid. And then if you leave this stoppered for a while, then basically you're going to see the entire inside of the flask adopting a color, the same color, which is due to the iodine gas that will be present inside the flask above the solid, all right? Now, there's a relationship between, oh, and of course, when it comes to sublimation, energy is required, and therefore you have what is known as the enthalpy of sublimation, delta H SUB, right? Which is the enthalpy required to transform a solid to a gas, all right? And there's a relationship between enthalpy of sublimation, enthalpy of fusion, and enthalpy of vaporization. And this is actually based on Hess's law. Let me show you here. So let's say we have iodine, which is a solid, and that is converted to a gas. No, I'm sorry, I started off wrong. Iodine, which is a solid, and that's converted to a liquid, I2 liquid, and then I2 liquid converted to I2 gas, right? So the enthalpy change for this conversion would be enthalpy of fusion, and the enthalpy for this here would be enthalpy of vaporization. So if you were to add these two equations together, this will cancel out with this, and therefore you're going to end up with I2 solid to form I2 gas, and this would be enthalpy of sublimation here. Excuse me, and that would be equal to the sum of these two, delta H of fusion plus delta H of vaporization. So that's a relationship between enthalpy of sublimation, enthalpy of fusion, and then enthalpy of vaporization. Enthalpy of sublimation would be equal to the sum of the enthalpy of fusion and vaporization. Okay, so that's the relationship between those two terms. Okay, or those three terms. So as I said before, that's a list. I went through that before. Okay, so let's talk about heating and cooling curves. And this is basically a plot of the transformation that takes place for a substance as you increase the temperature from the solid state up until the gaseous state. And basically, what is shown here is the heating curve, right? So let's say you have a solid here below its freezing point. In this case, I suspect it's water because the freezing point is 0 degrees. So let's say you have your solid below the freezing point and you start to heat it up, right? So of course, what will happen is that as you increase the temperature, well, as time progresses, you're increasing the temperature, and then you get to the melting point. So this is the point where you have the conversion of the solid to the liquid state. Now, what's going to happen at this point is that the temperature will remain constant. As long as you have solid present, the temperature is going to remain constant. So this line here represents the temperature at which you have the conversion from the solid to the liquid state. When all the solid has been melted, you'll only have liquid, and then what will happen is that the temperature is going to start to increase until you get to the freezing point. Now, unfortunately, it's cut off here, but what's going to happen is that when you get to the freezing point, then you have the conversion of the liquid to the gaseous state. So basically, the line is going to remain flat like this, and here you're going to have liquid and gas, right? So that flat line will persist until all the liquid is converted to gas, and then the temperature is going to start to increase beyond that, all right? So that's basically what the heating curve looks like in the case of water, or for that matter, for any substance, all right? I think there might be some variations for other substances, but essentially, this is what is observed. And basically, the reverse is going to happen when you do the cooling, all right? And that is what is being shown in this graph right here. Again, it's cut off up here, but I'm quite sure you can understand. It's the appearance of this graph here would be basically the mirror image of what we just did here in terms of the heating curve, all right? Okay, so let's move on now to a discussion. Oh, you know what? Let's stop here because it's now 10:48. So what we're going to do is talk about phase diagrams when we get back at 11 o'clock. Okay, so let me resume. Okay, so what we'll be talking about, oh, hold on 1 minute. Let me shut my door. Okay, so we're going to talk about this diagram right here. It's called a phase diagram. And basically, as you can see, it's a plot of pressure versus temperature. And what these lines represent are the different temperature and pressure values where the substance it's about exists in equilibrium between different states. So for example, this line here, B to A, represents the temperature and pressure values where there's an equilibrium between the solid and the gaseous state. This line here represents the temperatures and pressures where there's an equilibrium between the solid and the liquid state. And here, this line A to C represents the pressure and temperature values where there's an equilibrium between the liquid and the gaseous state, all right? So essentially, this line here basically indicates the melting points for, the sublimation temperature for the solid. This line here represents the boiling points for the liquid, and this line here represents the melting point for the solid, all right? That's basically under different temperature conditions. That's basically what those lines represent, all right? So this part here we call the fusion curve. This line right here, D to A, is called the fusion curve. B to A is called the sublimation curve. And of course, the vapor pressure curve would be A to C, all right? So that's basically what a typical phase diagram looks like. Now, there are some variations, as you're going to see, but most substances, basically, if you look at their phase diagram, this is what it looks like. Oh, I skipped over something here. The critical point, very important. We're going to talk about this later on, but basically, it's the temperature at which you cannot make a distinction between the liquid and gaseous state. So that is something that we're going to see shortly. We're going to spend some time talking about that. Okay, you know what? Okay, so here is, for example, the phase diagram for this compound, which is mercury 2 iodide. And as you can see, it's a bit of a departure from what we saw before, because mercury 2 iodide can exist in two different solid states, right? You have the alpha form and the beta form. So that kind of makes some changes to the phase diagram, as you can see here. Otherwise, it's pretty much the same, all right, as what we saw before, all right? So for example, at 127 degrees, you will have the coexistence of the alpha, beta solid forms, as well as the gaseous forms of mercury 2 iodide. At 259 degrees, you're going to have the equilibrium between the beta form and the liquid form. And as you can see here, you know, along this line right here, you have the equilibrium between the liquid and the gas. Here you have the equilibrium. This line here would be indicating the equilibrium between the beta form and the gas. And this line here will indicate the equilibrium between the alpha form and the gas. So that basically shows you the phase diagram for this particular compound. Let me see what we have. Here's another one for carbon dioxide. Again, it's a bit different from what we saw before, this part especially, but pretty much it's the same idea. So as you can see here, under normal, let me see here. At 1 atmosphere, right, the freezing point, or I should say the sublimation point of carbon dioxide is minus 78.5 degrees Celsius, right? So that's a reason why dry ice, which is carbon dioxide solid, that's the reason why dry ice converts to the vapor, because at 1 atmosphere and room temperature, which is higher than minus 78.5, you have the direct conversion of the solid state to the gaseous state, all right? Let's see, what else? And of course, if you want to have liquid carbon dioxide, then the pressure would have to be higher. And then this line here would be representing basically the boiling points of carbon dioxide. So basically the boiling point of carbon dioxide will range from minus 56.7 degrees to 31 degrees Celsius between the pressures of 5.1 atmosphere and 72.9 atmosphere. So the pressures would have to be relatively high for carbon dioxide to exist as a liquid. And then when the temperatures are the values represented here, then you'll have the equilibrium between the liquid and the solid at the corresponding pressures on the y-axis, all right? Okay, so let's see here. Okay, so now we're going to get into a discussion of the critical point I talked about, right? I made mention of. The critical temperature at that point is the highest temperature at which a liquid and vapor can coexist in equilibrium as physically distinct matters, states of matter, right? So basically up to that point, you can actually distinguish between the liquid state and the gaseous state. Now, beyond that, you won't be able to do that. But you have to have also the corresponding critical pressure, which is the vapor pressure at the critical temperature. So at that point, which is a critical point, is where you cannot make a distinction between the two. And that would be right here, right? Now, beyond that point, the state of the substance, we call that a supercritical fluid. That's what SCF stands for, right? So let's see here. So this is a picture showing you what happens in the case of water at the critical point. So this is room temperature, of course. You have water vapor molecules here, a small amount, and you have the liquid water here. And then as you raise the temperature to slightly below the critical point or the critical temperature, then you're going to have more vapor molecules in the space above. You're still going to have liquid water here. But when you increase the temperature beyond that point, then what happens is that you can't make a distinction. You see basically one phase here, all right? And that's basically what happens beyond the critical point, all right? So that's what is represented in the phase diagram at this point C right here, okay? Okay, so that's basically what the critical point is all about. Now, here's a phase diagram for water. Now, in the case of water, it's a bit different from other substances in that when you look at the line representing the equilibrium between the solid and liquid state, the line basically leans to the left. Most other substances, the line would lean to the right, right? And what that indicates is that as the pressure increases, then the melting point of the ice decreases, which is unusual in the case of water, because for most substances, it's the opposite that is true. And there's a reason for that, which I won't get into right now. It has to do with the fact that when ice melts, the structure it's due to hydrogen bonding, but basically what happens is that the structure in terms of the gross connections between the different water molecules, they tend to collapse and therefore the volume decreases as the pressure increases. That's all I'm going to say about that. It's a bit more detail, which I won't want to get into right now, but this is something that you need to remember in the case of water. This line here basically leads to the left in the case of water, whereas for most other substances, the line leads to the right. Okay, so let's talk about the type of forces that exist between molecules and ions later on. But for now, we're going to talk about molecules. We have what are known as dispersion forces. Dispersion forces are basically the force of attraction between the instantaneous dipole of one molecule and an induced dipole of another molecule. And these are also called London forces, named after this guy who basically offered this particular explanation for the fact that you have intermolecular forces between nonpolar molecules. And basically this is the explanation right here. So let's say you have a nonpolar molecule, right? Unpolarized, no separation of charge, all right? Then what happens is that because the electrons are always moving, if you could take a snapshot of the molecule at one instance, you'll find what is called an instantaneous dipole being formed, where temporarily what happens is that the electrons will accumulate on one side, making that sign negative, and the other side will be partially positive. The consequence of that is that, oh gosh, I have to turn this on. Hold on, give me 1 minute. Somebody keep calling me. Okay. Sorry about that, folks. So as I was saying, there'll be an instantaneous dipole being formed. Now, what will happen after that is that that instantaneous dipole will induce another dipole by pushing the electrons in the other molecule or attracting the electrons in another molecule towards the positive end of the first molecule. And as a result, there will be, let me draw this here. There'll be a force of attraction. So I'm going to put attractive force between those two instantaneous dipoles. So attractive force will occur, right? So this is what happens when it comes to nonpolar molecules, right? You have one dipole being formed instantaneously, and therefore it induces another dipole in another molecule, and there'll be an attractive force between the positive end of one molecule and the negative end of that instantaneous dipole. And then it's going to shift instantaneously. So basically, there'll be a shifting in the charge going in one direction, and the same thing will happen in the other molecule. And again, an attractive force will exist between the two molecules, all right? So that's basically what happens. Now, there's a very important term that you need to be aware of here, and that is the term polarizability, right? It's basically a measure of the ease in which the charge density of the electron is distorted by an external electrical field. And that's important because basically what you'll find is that the more polarizable the molecule is, the greater will be the attractive force between the induced dipoles, right? And therefore, that would impart certain properties such as higher boiling points, melting points, and so on between for a particular substance, all right? So that's basically what dispersion forces are all about. They occur mainly in molecules or between molecules that are nonpolar. Okay, so that's one important intermolecular force that you need to be aware of. We tend to see this type of force existing, for example, in hydrocarbons, alkanes, such as octane and isooctane. Again, we see that because these molecules are basically nonpolar, the intermolecular forces between them would be of that type, dispersion forces. And let me just say that dispersion forces are typically weak, all right? However, their strength can be affected by several factors. Now, one of them is the fact that, well, polarizability we talked about before. So the more polarizable the molecule is, then the stronger would be the intermolecular forces that would exist between them. Another factor in the case of alkanes that would affect dispersion forces is whether or not the carbon chain is branched or unbranched. So in this case here, we're dealing with an unbranched carbon chain, right? In this case here, we have we have a chain here, but we have a couple of branches, 3 branches off the longest chain, all right? What you'll find is that compounds of this type, where you have branches off the chain, they tend to not be as close to each other as possible, and therefore the dispersion forces will be weaker in these compounds. So therefore you'll notice that the boiling point of this compound, which is known as isooctane, is lower, 99.2 degrees, compared to the boiling point of octane, all right? So basically when it comes to alkanes, branching, let me write this down here, branching lowers the boiling point, lowers the boiling point. All right, so that's what happens in the case of alkanes and other organic hydrocarbons. Even though the formulas are still the same, right? They both have the same number of carbon atoms and hydrogen atoms, but because this one is more branched, then its boiling point will be lower. Okay, another type of intermolecular force that exists between molecules is what are known as dipole-dipole forces. And as the term suggests, these are forces that exist between molecules that have permanent dipoles, right? Sorry. So we're talking about molecules, excuse me, such as hydrogen chloride, right? Where you have a dipole that is present in this molecule. And what's going to happen is that in these substances, the permanent dipoles will line up such that the negative end of one will be attracted to the positive end of the other. So therefore, you're going to have the attractive force between these two ends. And that's the same right throughout the substance. All right. So that's what happens in the case of dipole-dipole forces being formed as a result of permanent dipoles being attracted to each other. What you'll find is that dipole-dipole interactions are stronger compared to the London dispersion forces that we talked about earlier, right? And another thing I need to mention while I'm at that is that even though you might have dipole-dipole interactions occurring here, you still have London forces occurring between these molecules as well. So in a molecule like HCl, this will have both dipole-dipole, dipole-dipole, and London, oh shoot, dipole-dipole, and London forces, all right? So you're gonna have those forces together, but the London forces in the case of permanent dipoles would be, I'm sorry, the dipole-dipole forces in the case of permanent dipoles would be the stronger of the two forces existing in substances such as hydrogen chloride and other polar molecules. Another type of force that can occur where you have dipoles present is that you can have dipoles inducing, I should say this, a permanent dipole in one molecule inducing a dipole in another molecule, and therefore you're going to end up with a dipole-induced dipole force, all right? So that can happen as well. Okay, so let's talk about predicting the type of physical forces that will exist in molecular compounds. As I said before, dispersion forces or London forces will always be present and become stronger with increasing molar mass and elongation of molecules, all right? So for example, if you compare the fluorine molecule to the chlorine molecule, right? I'm sorry, this should be the opposite in terms of the, it should be, hold on 1 minute. Okay, so if you compare fluorine to chlorine, right? What you'll find is that chlorine will have, because it has a greater molar mass, then basically greater molar mass, therefore will have a stronger London forces between their molecules, all right? Compared to fluorine, all right? And that's because chlorine has a greater molar mass, all right? Okay, and also in terms of the elongation of the molecules, as we said before, if you have branching in the molecules, and we're talking about here in the case of alkanes, organic hydrocarbons, and so on, what you'll find basically is that the more branching you have, the lower will be the boiling point. And that's because the molecules can be closely packed on top of each other, as in the case of single chain or non-branched molecules. Okay, so in comparing nonpolar substances, we look at two things. We look at the molar mass and we look at the molecular shape as factors that would influence the type of bonding or the type of forces that exist between molecules that are nonpolar. Now, when it comes to polar molecules, we have dipole-dipole and dipole-induced dipole forces that will be found, all right? The more polar the substance, as measured by the dipole moment, the greater would be the intermolecular forces that would exist between the molecules, all right? So that's basically what you look for when it comes to making certain predictions concerning the different types of forces that would exist between covalent molecules. Now, there's one special type of intermolecular force, which is actually a polar, or I should say a dipole-dipole type interaction, but it's unusually strong, and it's called a hydrogen bond, right? And the term hydrogen bond, the bond part of it, is a bit of a misnomer because it's not an actual chemical bond where electrons are being shared. It's an actual intermolecular force, but it's a very strong force. And this is a force that exists where you have hydrogen atoms that are bonded to a nonmetal, which is very electronegative, right? And in fact, the nonmetal atom that it's bonded to must be one of three elements. Must be either oxygen, nitrogen, or fluorine, right? So any compound which contains hydrogen bonded to any one of these atoms would be able to exhibit what we call hydrogen bonding. And in the case of hydrogen bonding, we're going to use the water here as an example. What is happening in the case of hydrogen bonding? I'm going to focus on this water molecule right here. So you have this oxygen bonded to this hydrogen, right? Now remember, the hydrogen has only one electron, which it shares with the oxygen here. So because the oxygen is so electronegative, it's going to pull the electrons that it shares with the oxygen towards it, right? So therefore the hydrogen here would be almost a bare proton, right? Because remember, hydrogen has only an electron and a proton in its atom. So if the oxygen is pulling away an electron from the hydrogen, then what you have almost left behind is a proton, and therefore this has a very high charge density. So let me write down here, where am I going to put this? Let me write here, high charge density. And because it has a very high charge density, then it will have a very strong attraction for the negatively charged oxygen on another hydrogen atom. So that strong attraction as a result of the high charge density of the hydrogen is what is called the hydrogen bond. And it's very strong, right? It's stronger than all other types of intermolecular forces, all right? So as a special bond, and what we're going to see later on is that this imparts particular properties to water. Water has an unusually high melting point and an unusually high boiling point, and it has other factors. In fact, one other property we talked about earlier about water, and this was back in chapter 6. I don't know if you remember, but in chapter 6, we talked about the fact that water has a very high specific heat, right? In other words, the amount of heat needed to raise the temperature of water by 1 degree Celsius is very high, for a fixed mass compared to other substances. And the reason for that is hydrogen bonding, because you need a relatively high temperature compared to other substances to basically break the forces between them, between the molecules, which would be the hydrogen bond, in order to achieve the same temperature change, all right? So that's just another property that can be explained based on the hydrogen bonding phenomena. Hydrogen bonding is also important when it comes to organic and biological molecules. For example, if you have done biology before and you learned about the structure of the DNA, you should have learned that the DNA structure is actually held together in large part as a result of hydrogen bonding between the hydrogen of one atom and some other electronegative atom in another part of the structure. So hydrogen bonding is very important in nature. Our very lives actually depends on it. Okay, let me see here. So this is showing you the structure of ice. Again, this is due to hydrogen bonding. And the result of this is that ice has an open structure. And that's the reason why ice has a lower density compared to water. The density of ice is about, if I remember correctly, of course, it depends on the temperature. But if I remember correctly, the density of ice is about 0.7 gram per mil, maybe a little bit more or less. And that's the reason why, the term tip of the iceberg is kind of reflective of something factual about the nature of ice. Because if you go to, those cold regions where icebergs exist, basically the bulk of the mass of the ice is under the water. And what you see as the iceberg is basically 30% of the total mass, right? So you might see a huge iceberg in front of you, but the mass of the ice that is underneath the surface is much larger, right? And that's why ships are equipped with, certain sonar equipment so that they can detect the mass of the iceberg beneath the surface, so that they can avoid collisions with icebergs, which is what happened in the case of the Titanic. They didn't have the equipment back then to detect the large mass of iceberg that was beneath the surface. So that again is related to, believe it or not, hydrogen bonding. Okay, so I just mentioned this actually. Solid water is less dense than liquid water due to hydrogen bonding. And I mentioned this already, hydrogen bonding is also the reason for the unusually high boiling point of water. And I mentioned this as well, proteins, right? So this is the DNA structure, and this is the hydrogen bonding I'm talking about here, between the hydrogen bonded to the nitrogen here, and the oxygen here, and there are other hydrogen bonding here, here, and so on. So that basically holds the whole protein structure together in this case. I'm trying to figure out if this is a DNA structure. I think it is, all right? So that's, again, reflecting the importance of hydrogen bonding. Okay, another effect of hydrogen bonding is that you can have the formation of what are known as dimers. And this is particularly true in the case of organic acids, right? So what we see here is two acetic acid molecules that are linked to each other by hydrogen bonding. So this is one molecule of acetic acid here. This is another molecule of acetic acid here. And you see that there's a hydrogen bonding occurring between this hydrogen and this oxygen and this hydrogen. And what this is reflected in the fact that whenever somebody does an experiment to determine the molar mass of acetic acid, in some cases, what you'll find is that the calculated or measured molar mass of acetic acid is double what it should be. And that's because acetic acid doubles up to form dimers in this way due to hydrogen bonding. You can also have intramolecular hydrogen bonding as seen in this case. Now this compound here is salicylic acid. And as you can see here, you have the hydrogen here forming a hydrogen bond with this oxygen here in another part of the molecule. So this is an example of an intramolecular hydrogen bonding taking place in this particular compound. Okay, another consequence of hydrogen bonding is what is known as surface tension. And here's a definition of surface tension. It is the amount of work required to extend a liquid surface and is usually expressed in joules per meters squared. So that's the consequence of the fact that the molecules at the surface will have interactions with molecules below the surface. And if the hydrogen bonding is strong in these cases, then basically more energy will be needed to separate these molecules at the surface, all right? Now here are two terms that you need to be aware of: adhesive forces and cohesive forces, right? Adhesive forces are intermolecular forces between unlike molecules, such as the forces that exist between water molecules. And then we have cohesive forces, which are intermolecular forces that exist between like molecules, such as the force that can exist between water and the surface of the glass container that they're in. Let me see. Oh, I'm sorry. Yes, sir. Is somebody asking a question? Okay, let me mute this person here. Okay. Let me see here. Okay, so the reason why I mentioned adhesive and cohesive forces is because that's important to understanding why a meniscus in, like if you pour water in a graduated cylinder, why the meniscus have a curved shape like this, an upward curved shape, right? Well, the reason why is because in the case of water, right, which is what we have here in this tube, there'll be an attractive force that exists between the water molecules and the glass surface, which will be stronger than the attractive forces between the water molecules themselves, right? So therefore, as a result of the fact that the adhesion forces would be greater than the cohesion forces within the water, the curve would be like this, where the water will be attracted and pulled up the glass surface. Now, in the case of mercury, the meniscus is the opposite way. It's like this, right? Which is the opposite of what we had here in the case of water. And the reason why this is the case is because in the case of mercury, the cohesive forces are stronger than the adhesive forces. So therefore, the attraction between the mercury atoms here beneath the surface of mercury will be stronger compared to the attraction between the mercury and the glass walls of the container. The competition between adhesive and cohesive forces can also be seen to explain why water will move up into a capillary tube. It's the same idea. Basically, again, in the case of the glass tube and the water moving up into it, the water will have a greater attractive force for the glass surface, which would be the adhesive force, which would be greater than the cohesive forces that exist between the water molecules. So therefore, if the tube is narrow enough, what will happen is that the water will move up into the tube. All right. So all that I've described here is as a result, believe it or not, of intermolecular forces, and in the case of water, hydrogen bonding. Okay, let's talk about viscosity, right? Viscosity is a measure of a liquid's resistance to flow. And of course, liquids that flow easily are said to be mobile. And we measure viscosity in terms of units of poise. And typical liquids tend to have viscosities measured in centipoise, all right? And viscosity, even though it's not mentioned here, is a function of the intermolecular forces. So basically, the greater the intermolecular forces that exist, then basically the lower would be the viscosity, all right? Okay, so this is a summary of what we have described here in this chapter so far in terms of the different forces. For nonpolar molecules, basically the intermolecular forces would be dispersion forces, and they tend to have low melting points, and they tend to also be soluble in nonpolar solvent. And these are some examples of different substances that display this type of forces. Then when it comes to polar molecules, these are the forces that exist. You have dispersion forces. You also have dipole-dipole and dipole-induced dipole attractions. These tend to have low to moderate melting points, soluble in some polar and some non-polar solvents, and these are examples of compounds displaying that type of bonding. And then we have hydrogen bonding, which is a special type of dipole-dipole interaction. And these compounds tend to have low to moderate melting points, and they tend to be soluble in hydrogen bonding and some non-polar, some polar liquids. And these are examples of compounds which display that type of bonding. Okay, now we haven't covered these yet. We're going to cover them shortly. So what I'm going to do is skip to the next slide, but just to indicate, we'll be talking about covalent, ionic, and metallic bonding. And actually network covalent, I meant to say, network covalent, ionic, and metallic bonding. And we're going to see how those compare to the type of forces that exist between molecules. Okay, so let's talk about network covalent solids. And these are substances that have an extended network of covalent bonds right throughout a crystalline solid. And these forces are very strong. A good example of this is diamond. So what you're looking at here is a small part of the structure of diamond. Diamond consists of carbon atoms, and each carbon atom is covalently bonded to 4 carbon atoms, right? And that continues throughout the entire structure of diamond, all right? And this is the reason why diamond is the hardest known substance ever. Well, hardest known element, at least. I don't know, I think silicon carbide is harder than diamond, all right? And it has the same structure, a similar structure as well. Allotropes. So carbon, or diamond, I should say, is what we call an allotrope of carbon. Allotropes are basically 2 or more forms of an element that differ in their basic molecular structure. So this is one allotrope of carbon. There's another allotrope known as graphite, and there are others as well, but those are the 2 most common allotropes of carbon. In this particular allotrope of carbon, as I said before, this is basically how the bonding occurs, and as a result, it imparts certain properties to carbon in this form, including that it's a very hard structure. That's why diamond is used, for example, to cut glass, because it's the only substance that's hard enough to do that without any, without much in terms of, breaking it or anything like that. And there's just a mention here that sulfur is also another element that exists as an allotrope or allotropes, all right? So as I mentioned before, this is one allotrope of carbon, and this is another allotrope of carbon, which is graphite. And you see the difference between them. In this case, the carbons are at the center of a tetrahedral arrangement of other carbons, whereas in the case of graphite, the carbons are arranged in hexagonal sheets. So you have one sheet here, one sheet here, one sheet here, and there's a distance between the sheets. And the thing about graphite is that graphite is a very good conductor of electricity. In fact, it's the only non-metallic element that's a good conductor of electricity. And the reason why is because in the case of graphite, you have a delocalized system of pi electrons that exist between the sheets, all right? And those electrons, because they're delocalized, they're mobile, and therefore they can conduct electricity when you apply a potential difference to that material. So therefore, for that reason, graphite is a very good conductor of electricity, all right? In the case of graphite, the carbons here are sp2 hybridized. In the case of diamond, the carbon atoms are sp3 hybridized. So that's the reason why there's a tetrahedral arrangement of carbons around each carbon atom in the case of diamond, and in the case of graphite, each carbon has a trigonal planar arrangement of other carbon atoms linked to it, all right? So that's the difference between these two particular allotropes. Okay, and then we're going to talk about crystal lattices, which exist in ionic compounds, right? And what you'll find, and also exist in some other non-ionic compounds. Now, what do we mean by a crystal lattice? Basically, we're talking about a structure where you have repeat units, all right? So for example, in this hypothetical situation, if you go along the chain here, you'll see that after so many units, you see the same, after so many items here, you see the same pattern emerging right throughout. It's the same thing when it comes to certain ionic compounds, right? In fact, in ionic compounds, you can identify what is known as a unit cell, which is basically one repeat unit that you observe throughout the whole structure. So for example, if you have ions arranged in this structure right here, then one unit cell would be simply this region right here, this cube. And that repeats in all directions, X, Y, and Z directions, all right? Okay, so let's look at the different types of arrangements. You have the simple cubic cell, which is the simplest unit cell that can exist, right? Very simple. Basically, it's 4 atoms or ions occupying the corners of a cube, all right? And then you have what is known as a body-centered cubic cell, which has 4 atoms at the corners of a cube, and then you have a middle one at the center, like that. And then you have the face-centered cubic structure, where you have 4 atoms at the corner of a cube, and then in the middle of each face of the cube, you have another atom, right? So that is here, 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 down the bottom here, and on the other side, all right? So these are the general unit cell arrangements that one can identify. There are others as well, but you know, we'll just basically limit our discussion to the ones that we just discussed here. Okay, one important thing you need to be able to identify when it comes to unit cells, and that is the coordination number, which is the number of nearest neighbor particles to a single particle in the crystal. So for example, in this case here, in this particular arrangement, as far as this atom is concerned, the coordination number for this atom is 6. 1, 2, 3, 4, 5, 6, all right? And that is the case for a simple cubic structure, all right? Which is what is represented here, okay? So that's basically what the coordination number is. It's the number of nearest neighbor to one particular atom in that arrangement. Now, when it comes to crystals, you can have different types of packing arrangements, right? The understanding here is that basically when these substances assemble, or when these particles assemble, they try to be as close to each other as possible. Theoretically speaking, there are 2 possibilities. For one layer, you can have an open packing, which looks like this, and then you can have the closed packing, which looks like this, all right? And you can clearly see that in the case of the closed packing, on average, the particles are closer to each other compared to the open packing, because you can see that the spaces here, in the case of the open packing, is larger compared to the closed packing. Then when it comes to filling in or adding another layer, there are 2 possibilities, right? When it comes to the closed pack structure. You can have basically, well, let me put it this way. So if you put these particles here on the second layer, as you can see here, then you're going to have what are known as 2 types of holes. You have what are known as the tetrahedral holes, which are these holes right here. And then you have the octahedral holes, which basically are spaces below that are not occupied by any particles in the bottom layer. All right. The tetrahedral holes, you can see clearly the bottom layer particles present or can be seen. All right. So that's basically the difference between those two holes. And that means that when you're adding another layer of particles, then there are two possible positions they can occupy. They can occupy the region above the octahedral holes or the region or the space above the tetrahedral holes. So let me see if I have that here. So when they cover the when the next layer cover the tetrahedral holes, this is what you have here. And this is called a hexagonal close packing. All right. So that is what is being shown here as a side view. All right, so that's a hexagonal close packing. And then if you have the next layer, instead of occupying the tetrahedral hole, they occupy the octahedral hole, then the arrangement is this, and it's called the cubic close packing. All right. In some textbooks, and I think I may have had it here, I thought I did. They call this part the AB arrangement, and that's because these particles here, which forms the third layer, are exactly above the particles in the first layer. So that's why they call it AB arrangement. And in this case, they call it ABC arrangement, because when you get to the third layer, which would be the C layer, it occupies the hole or covers the hole in the A layer, in the B layer, and therefore the arrangement of the A, B, and C layer would be different. Whereas in the case of the hexagonal close packing, the arrangement of the A layer, of the first layer and the third layer would be the same. So that's why this is called AB, while this is called ABC. So this is called cubic close packing, right? And this is called the hexagonal close packing. Okay, let me see here. And then what you'll find is that whichever type of packing that would be adopted by the different compounds is largely related to the ratio of the cations to the anions in each of these cases. And it was found experimentally that when this ratio lies between 0.225 and 0.414, then basically the tetrahedral holes would be filled, and that would be due to that would result in the formation of the hexagonal close packing. And then when the ratio lies between 0.414 and 0.732, then the arrangement would be the cubic close packing in that case. So that's basically what happens when it comes to the layers, how they are assembled in ionic crystal structures. Okay, now if you look at some examples here, in the case of cesium chloride, this is basically the arrangement. You have the cesium ion in the middle, and then you have the chlorine atoms occupying the corners, right? Now, you might be wondering, well, the formula for cesium chloride is CsCl, right? How is it that we have a 1-to-1 ratio between the cesium and chlorine? Well, the answer is that each of the chlorine atoms occupying a corner is actually being shared between, let me see, 1, 2, 3. Okay, so each of these here, each chlorine atom is being shared between 8 cubes. So therefore, basically this here represents 1/8 of a cesium, 1/8 of a chloride ion, and there are 8 of them, so 8 times 1/8 would be equal to 1. So basically each unit cell contains 1 chloride ion. So therefore, the ratio of chloride to cesium ions would be 1-to-1, all right? And then here, in the case of sodium chloride, where it's a face-centered cubic, what you'll notice is that each sodium, well, let me see here. Okay, let me use this here. This is more simple to look at. So if you look at, let me see here. So this is your sodium atom, and the sodium atom is surrounded well, the coordination number is 6. So you have 1, 2, 3. Let me circle them. 1, 2, 3, 4, 5, 6. All right. In this case here, let me see what the arrangement is. So basically, you have a sodium atom in the middle, and you have a sodium atom here, here in this unit cell, here, here. Let me count them. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. It's kind of not clear here to me, but basically, the ratio, if you look at the sharing arrangements, the ratio of the sodium to chloride will also be 1:1. It's a bit more difficult to see in this case, as opposed to in the case of the cesium chloride. So I'm just going to skip that for the time being. But for now, you should just appreciate that it's a 1:1 ratio between the sodium and the chloride ion. Now, what is being shown on the screen here, and I won't go into any details as far as this is concerned, because this is mostly physics. But this is basically showing you how the arrangement of atoms or ions in a crystal is determined, especially with respect to the distance. Basically, it uses X-ray. It's a process called X-ray diffraction. X-ray diffraction. And basically, in this method, basically, it's used to measure the spacing between the ions or atoms that are present in the structure. So I won't go through all the details. I think if I remember correctly, there's an equation which is 2D is equal to n lambda sine theta, if I remember correctly. And basically based on this equation, you can find out what D is, and D would be basically the distance between the nuclei of the different ions that are present in this crystal structure. Oh, here's the equation right here, actually. N lambda is equal to 2D sine. So I had it wrong. So let me just cross it out. Let me cross this out here. Okay, so this is the equation that is used to determine D. And once they determine D, then they can figure out the type of arrangement, if it's cubic close packing or hexagonal close packing, whatever. Okay, so that basically represents the end of chapter 11, which is the end of the course. Okay, so let me see. What I'm going to do is, well, firstly, I'm going to publish, I think I published some of them already. Let me see here. I'm going to publish some of the assignments based on chapters, let me see here. Oh, it's already published. Okay, the only thing I haven't published here is chapter 11. And it won't be much because actually what there's other things I need to discuss. I should have discussed in chapter 11, but in the interest of time and knowing that you guys have a lot on your plate, I won't go into that part of it because there are some calculations, problems that goes along with chapter 11, which I'm not going to get into for you guys. So basically, what's going to happen from here is this. Hold on. Let me do. Let me just check something here. Okay, so I've posted so far all assignments up to 43. So I'm going to post the rest of them, assignments 44 through 52. And today's what? Today's Wednesday. So basically these will be due on, I'm going to make them due on Friday. So Friday will be the, what date? Oh, actually, let me extend it to the 20th, all right? So, the assignments will be due on the 20th. And I'm going to post the final exam as well. And I'm going to let that be due on, because I have to submit the dates by, I have to submit the grades by the 24th. So I'm going to need some time to grade them. The final exam will be due on the 22nd. And also test number 3 will be due on the 22nd as well. So I'm going to post test number 3 and the final exam. I'm going to do that tomorrow. All right, so look out for that tomorrow. And make sure that they're completed and turned in by the 22nd, because I'm going to spend all of the 23rd to grade them and make sure that your grades are in place, so that by the 24th, let me just confirm the date for before I say the wrong thing.
Will we have a third test?
Yeah.
Okay.
Mm-hmm.
And what
Okay, right.
chapters are they going to cover?
Okay, for the third test, because the second test covered chapter 3 to 5, right? So the third test will cover chapters, hold on. I would say the third test will cover chapter 6 through 8. All right? And then the final exam will cover everything, all the way to 10.
Okay.
All right? So 6 through 8 would be test number 3. And that would be due on the same day as the final, which is the 22nd of July. All right? So I'm going to try as much as possible to grade your assignments and send you, well, I have some that I've graded already, which I'm going to send to you today, after lab today, all right? So that you can have that to review. And then the others, there are some more assignments that are due on Thursday. I'm going to try to grade through that as quickly as possible so that you can get that to review as well. And I'm also going to I'm also going to post the answer keys as well. All right. So basically, that will be what will be happening between now and next week. We'll all be busy, kept busy during that time.
So will there be another lecture Monday?
I don't know. What do you guys need a review? I'm I'll be available, right? So, I can make myself available here. I can help you out with the assignments, right? If you have any questions. In fact, what I'll do is I'll make myself available tomorrow from 2 to 5. I'm not sure about Friday yet. But Monday, I can make myself available during the regular class time.
Okay.
All right. So if you have any questions, you can call me on Skype. Contact me on Skype for that purpose.
Gotcha.
All right.
And before we finish up the lecture,
Mm-hmm.
there were 2 things that I wanted to bring up on the second test.
Okay.
Because there were 2 questions that seemed like they may have had typos. Trying to find.
Okay, because I haven't graded that yet, unfortunately. So maybe you can mention to me what you think the typos were.
Oh, one of them has to do with the hand-drawn apparatus page.
All right, hold on, 1 minute. So let me see here. Tests. Okay, so you're talking about test number 2.
Yeah.
Let me see here.
And it
Okay,
says
what number? What question number?
the numbers are and letters are all over the place. Like I said, it's the hand-drawn apparatus, and it is asking us to calculate the final pressure of the mixture when the reaction goes to completion.
All right, hold on. Let me check it. Let me check it.
It
Oh, that one. Okay.
like wouldn't it be 3H2 plus N2, not 3N2 plus H2?
Oh. Oh, yes, that's a typo. Yeah, that's a typo. Okay, that's a typo right there. Yeah, it should be N2 plus 3H2. That is a typo. Okay, let me see here. All right, tell you what I'm going to do is I will skip that question when I'm grading it. Because, you know, in fairness to you guys, you probably don't realize, even though, strictly speaking, whenever you see a balance, whenever you see an equation, it should be balanced, but, or you should check to make sure it's balanced. But because of that, I will skip that question. Okay, any other issues with this test, you said?
And with the net ionic equations,
Okay, so let me see here. Net ionic equation.
the one marked as number 3 in that set. From what I understand, the aluminum is always a charge of +3.
Yep. Oh, I see what you're saying. So that should be Al2CO3.
Yes.
Okay. Okay. All right, I'm going to skip that one as well.
I mean, I did it as if it was a 3
Mhm.
and marked it.
Okay.
I just wanted to bring those up.
Yeah, I
The
understand.
one that might not have caught it.
Yeah. Yeah. Yeah, I mean, in fairness to, you know, everybody else, I think I'll just skip that as well because, you know, it's my responsibility to make sure that these, you know, these formulas are accurate when I type it up. So I'll take that into account. All right. Okay. Any other questions? Any other questions? Okay, so that's it for today. So I'll see some of you later on, and some of you I may see next week if you have any questions during lecture time. All right. So that's it for today, and enjoy your weekend.